Having looked at the implications of quantum mechanics for atomic structure, namely energy levels, sublevels, orbitals, the strange shapes, the weird things electrons do, we're going to look now at some of the experimental evidence for quantum mechanics and some of its further implications. To do that, we have to understand electromagnetic radiation. Electromagnetic radiation is a form of energy. It comes in waves of alternating electric and magnetic fields, and as those wavelengths change, we get different types of electromagnetic radiation, and they present themselves on what is known as the electromagnetic spectrum. The spectrum is either a diagram of increasing wavelength or increasing frequency, which are the two primary modes of measuring electromagnetic radiation. The longest wavelengths have the shortest frequencies and the lowest energies, and that is a relationship you should probably get settled in your brain pretty well. Long wavelengths, low frequencies, low energies. Short wavelengths, high frequencies, high energies. Wavelengths are just that, the length of the wave. We'll look at that more specifically in the next slide. And frequency is the rate at which a wave cycles as it propagates through space. So if you have a really long wave, as it's moving through space, it'll take a long time to start the pattern over. If you have a very short wave, the pattern will start over many, many times in a very short span. And so all the way on the left there, we have our radio waves. Radio waves are the lowest energy electromagnetic radiation. They're from lengths the size of a few meters to hundreds of meters. Radio waves obviously used pretty significantly in radio signals, like to your car radio. There are two bands on the car radio, right? AM and FM. FM radio stations are measured in what are called megahertz. Mega is 10 to the 6, which means a million. So you think of a radio station like 98.9 FM. That's 98 million megahertz or hertz cycles per second as that wave moves through. AM radio stations, so if you listen to sports on radio at all, you usually have to flip over to the AM dial, and so one of the AM channels is 810. AM stations are measured in kilohertz. Kilo is 10 to the third. So 810 kilohertz is 810,000 cycles per second. So you can see why much shorter much lower frequencies, 810,000 versus 96 million, you end up with much lower energy on the AM side. And when you drive under a bridge listening to an AM station, you end up losing the signal a little bit. Okay. From radio waves, then we go into microwaves. And again, notice how there's this kind of fade in, fade out overlap. There's nothing that suddenly happens that turns a radio wave into a microwave. We label different parts of this scale, different things based on our perceptions or how we use them. So a very short wave, radio wave, is roughly the same energy or the same type of wavelength as a very long wavelength microwave. And depending on how it's used, one scientist might call it a microwave, one might call it a radio wave. Of course, we use microwaves in microwave ovens. That works because the particular frequencies we use are the exact right frequencies to cause water molecules to rotate. So you turn electromagnetic energy into kinetic energy, and that heats up your food by those water molecules spinning around in there. Radar, cell phone towers also use microwave radiation to get cell signals to you. Don't worry, it's not going to cook your brain. They're different wavelengths. Infrared radiation is generally associated with heat. There are animals in the animal kingdom that are actually adapted to sense things in the infrared spectrum, so mainly like pit vipers are a type of snake that have little pits in their face. They can actually pick up the heat signatures from little scurrying, fuzzy, warm-blooded rodents that they might want to have for dinner. And that tiny little sliver you see there after infrared is the only thing our eyes and brains are able to pick out of this whole thing, and that's the visible spectrum. And so the visible spectrum is probably the highest amount of energy, or the most plentiful amount of energy the sun gives out, which might be one of the reasons why we're adapted to gather that signal. So that's the rainbow, Roy G. Biv, red on the low energy side to purple on the high energy side. And you know that because after purple comes ultraviolet, right? So it's more than violet. And that is another form of energy that the sun gives off. That's the kind of thing that causes sunburns. So, wear your sunscreen, wear a hat. From ultraviolet, we then go to soft X-rays or X-rays in general. Soft and hard are just difference between energies. And of course, we use those to scan for breaks in bones and whatnot. And then beyond that are gamma rays. Gamma rays are particularly dangerous mainly because they're high energy and it might turn you into the Incredible Hulk. Okay, so those are kind of the different types of electromagnetic radiation. Let's talk about the different properties of a wave in general, and then we'll apply that to electromagnetic waves. The highest point on a wave is called the wave crest. That's the very top of the wave. The lowest part is called the trough. So highest point, trough, lowest point, or highest point, crest, lowest point, trough. The distance between any two crests, or the distance between two troughs, or the difference between any two successive points is called the wave length. The distance from the reference point to the crest or reference point to the trough is called the amplitude. If we're talking about sound, amplitude is loudness. If you're talking about light, it's how bright something is. If you're talking about the ocean, it's how surfable a wave is. And then the last thing we need to talk about is frequency. So if you pick a particular point in space, frequency is about how does that wave move, or what does it look like for that wave to move through space? How many times does that wave cycle through as it's propagating? A wave moving through space is called propagation. And so frequency is measured in cycles per second. And if you've got a shorter wavelength moving the same speed, then in the same amount of time, you're going to get more cycles to pass that point. So you're going to have a higher frequency. Okay, so things get a little more complicated when you're talking about an electromagnetic wave because it's not one, but two waves, right? So you have alternating electric and magnetic fields. So the electric field there in blue, the magnetic field there in red. They're perpendicular to one another. And then in the third axis, perpendicular to those two things, is the direction in which the wave propagates. And so again, there is always there's always a magnetic field with the electric field. Electricity and magnetism always go together. To convert between wavelength and frequency, we have this equation where that upside down y is called a lambda. It's a Greek letter. It stands for wavelength. The F is frequency, although you will also see that kind of V with the tail on the left side, which is the Greek letter nu, N-U. And nu or F or the italicized F will be used for frequency. And then C stands for the speed of light, because electromagnetic radiation, all of it is essentially light. Visible light is the part that we can see, but really any part of the electromagnetic spectrum can be considered light, and everything moves, or all electromagnetic waves move at the speed of light, and which is a particular value in a vacuum. Wavelength is going to be measured in meters in the SI system. It's a length. It's actually a distance in space. Frequency, as we mentioned, is 1/seconds or cycles per second. We don't actually write the cycles down because it's not a unit. It's just counting how many times something happens. So the unit is per second. In the SI system, we convert that into a derived unit known as hertz. Hz is the abbreviation, and so hertz just means cycles per second. Speed of light in a vacuum is 3 times 10 to the 8th meters per second. 10 to the 6th is million, so this 300 million meters every second that light travels. That's a pretty good chunk of time, or a pretty good chunk of distance that's covering in a pretty small amount of time. This is what it would look like for the waves to propagate, right? So the electric and magnetic fields are just oscillating high, low, high, low, high, low as they move through space. And different receptors, again, your eyes are one of them if it's visible light, pick up the difference in time between the height and the trough of that magnetic field and electric field. Okay, we're going to be focusing particularly on the visible spectrum of light. And again, if we look at this diagram, visible spectrum goes Roy G. Biv. This one's going a little bit backwards. You have to be careful when looking at these diagrams because some of them go with increasing frequency, low frequency to high frequency, which is low energy to high energy. Some of them go increasing wavelength, low wavelength to high wavelength. And if you're doing that, then your energy is flipped. You're going from high energy to low energy. So notice we have our purple over here and our red over here. Remember, ultraviolet is more than violet, so it's always higher energy on the other side of purple. But here's another version of the spectrum, right, that's got purple on the right and red on the left. So make sure you're not just assuming that everything increases to the right because you have that inverse relationship. Okay, so what you need to be able to do with this is you need to be able to convert between wavelengths and frequencies. And again, we do that with this equation, C equals lambda nu, or C equals lambda f. So C is always the same, 3.00 times 10 to the 8th meters per second. It's a constant. So you'll always know what that is. Either you're given the wavelength and asked to find the frequency, or you're going to be given the frequency and asked to find the wavelength. In this case, it leads with what is the frequency. So 3 times 10 to the 8th meters per second is our speed of light. 6.930 times 10 to the 7th meters is our wavelength. We're trying to solve for frequency. You should go ahead now and pause the video. You should do the calculation yourself. Make sure you can round it for significant digits. Make sure you know what the units are supposed to be. Go ahead and do that. Write it down and then play the video to check the answer. Okay, so our first step, we want to divide both sides by that wavelength. The wavelength then is going to cancel on the right side, and on the left side, our meters are going to cancel. Okay? Remember, in your calculators, you're going to go 3e8. Don't do times 10 to the caret. Use that EE or exponential key. Divided by 6.930 times 10 to the 7th is 6.930 E7. Again, before you hit equals, think about what the answer should look like. Think about what the exponent is going to be. Well, when you have powers of the same number and you divide, you subtract. So this ought to be in the neighborhood of 10 to the 1, which would just put it in the tens place. Now, when you divide 3 by 6, we get a number less than 1. So that's going to drop us into roughly the ones place. And sure enough, when we do the math, you're going to round it to 3 significant digits because of the 3.00. You get 4.33 hertz for your frequency. Don't forget your sig digs, don't forget your units.